Let's have a look at this awesome question on gravitational fields. If the mass of the moon is m by 81, where m is the mass of the earth, find the distance of a point where the gravitational field due to earth and moon cancel each other out. And we have to find the distance from the center of moon. So somewhere in between earth and moon, there is a special point at which the net gravitational field due to earth and moon is 0. And we have to find the location of this point from the center of the moon. Given that the distance between the centers of earth and moon is 60 times r, where r is the radius of the earth. So we know what is the distance between the center of moon and center of earth. It is 60 times r. Okay. So this is the given situation, and somewhere in between moon and earth, there is a special point at which the gravitational field due to moon and gravitational field due to earth cancel each other out perfectly. And we have to find the location of this point from the center of moon. We have to find this value of x. Okay? Yes. Now, if you look at this point from the center of earth, it is actually 60r minus x distance away from the center of earth. Okay? Yes. Now, the question talked about something called gravitational field. Don't be scared with this term. You can just see that value of gravitational field is nothing but gravitational force on a unit mass. Okay, so that's how you can quickly find the value of gravitational field. Gravitational force on a unit mass. Now, this point is very special at which the gravitational fields are cancelling each other out. Now, let's see the magnitudes. E1 should be equal to E2. Now, gravitational field due to moon. What is the value? It is G times mass of the moon, m by 81, divided by distance from the center of the moon whole square. So divided by x square. This is E1. Now gravitational field due to earth. What is the value? It is G times mass of earth. This is capital M, divided by distance from the center of the earth whole square. So this is 60r minus x whole square. Good. Now you can notice something will cancel out. G cancels out, M cancels out, and what are we getting? We are getting 60r minus x is equal to 9x. This means x is nothing but 6r. Okay, we got the value of x. So if this point is about 6r distance from the center of the moon, then at this point the net gravitational field would be 0. Okay? Yes. So we got the answer. Option D, 6r is the right answer for our question. Let's have a look at this question, which says that a thin rod of length capital L is bent to form a circle. So we have a rod and we bend it to form a ring. Nice. Its mass is capital M. So mass of the rod was given to be capital M. Mass of the ring will also be capital M. What force will act on mass small m placed at the center of the circle? So if we place another mass which is small m at the center of this ring, what will be the total force on this small m? Now, when we are talking about the total force, we mean total gravitational force. Okay? Yes. Now, let's try to imagine if there is a net force on this mass, in which direction should we get the net force? Should we get the net force towards east or towards west, towards north, towards south? In which direction should we get the net force? You will say, well, it is symmetric. Everything is symmetric in this case. So we cannot pick any particular direction. We have no reason to pick one particular direction because everything is symmetric. Yes, this indicates something. this indicates that the net force on this small m will be 0. Now let me show you mathematically how it is 0. Let's say we take an element dm over here. So this element is of some mass. It will attract small m towards itself, right? Right. Let's take another element of the same mass dm opposite to the previous element. Now this element will also attract small m in this direction, in its own direction. Yes, yes. Now you can see for this pair of elements, if we talk about the total force on small m, it is 0. So these forces are cancelling out in pairs, and there are multiple pairs. For example, here is another pair, and we can see the net force is cancelling out due to these pairs. So if we talk about all the possible pairs on this ring, then we can see that the net force on small m will be 0. So this is another way to understand. The third way is, if you remember, the net gravitational field at the center of a ring whose mass is distributed uniformly is 0. So if you remember this, then also you can say if the net gravitational field is 0, net force at the center will be 0. Now we can say option D, 0, is the right answer for our question. If the gravitational potential due to Earth at infinite distance from it is 0, the potential at point P is minus 5 joules per kg. Suppose we arbitrarily assume the gravitational potential at infinity to be plus 10 joules per kg, the gravitational potential at point P will be. Now I know you haven't understood a word of a question, so let me repeat the question again. Now this question is based on gravitational potential. And now let me show you what the question is talking about. Now we have two systems in this question. In one system, the gravitational potential at infinity was defined to be 0. Now we can choose our reference point wherever we like. Generally, we take the potential at reference point to be 0. So earlier in the first convention, we have chosen our reference point at infinity. The potential at infinity was defined by us to be 0. Okay. The potential at point P was minus 5 joules per kg. Point P is close to Earth. Now we change our convention. In our new convention, the potential at infinity was defined as plus 10 joules per kg. Let's call it V infinity dash. Now we have to find in our new convention what will be the potential at point P. What will be the Vp dash? This is the question. Understood? Yes. Now just pay attention to this little formula. We define change in potential between 2 points. The 2 points we are choosing, one point is at infinity and one is point P. So let's define the change in potential between these 2 points. So Vp minus V infinity is given by work done per unit mass by the external force in bringing the mass from one point to another point. So Vp minus V infinity is work done per unit mass by the external force in bringing the mass from infinity to point P. Okay, this is how we define change in potential. Now this thing is very interesting. Change in potential depends on work done by the external force and the mass. Now, have we changed the mass? No, we haven't changed the mass. Have we changed the work done by the external force in bringing the particle from one point to another point? No. Work done by external force will also be same. Even if we change our convention, this work done is not going to change. This is mechanical work done. This work done is done against the gravitational field and we are not altering the gravitational field. Okay? Yes. So we know this thing is constant. Yes. So this thing, as it remains constant, even if we change our convention, then it doesn't matter. The change in potential between the 2 points will be defined in exactly the same way. Now we have V infinity dash in our new system and Vp dash. So we have Vp dash minus V infinity dash. Okay, this is the difference in potential between the 2 points. Although we have changed our convention, but the difference in potential will remain the same. So you can see Vp minus V infinity is equals to Vp dash minus V infinity dash. All right, yes. Let's put the values. Vp was minus 5, V infinity was 0 in the old convention. In the new convention, we have to tell what is Vp dash. In the new convention, V infinity dash is plus 10. From this, we can obtain what is Vp dash. From this, Vp dash is coming out to be plus 5 joules per kg. Good. So we got the answer, plus 5 joules per kg. Option B is the right answer for our question. Two concentric shells have masses m1 and m2 and radii r1 and r2, where r1 is less than r2. So you can see the two shells. What is the force exerted by this system on a particle of mass small m if it is at a distance of r1 plus r2 divided by 2 from the center? So we place a particle in between these shells. This is point P, and at this point we place the particle of mass small m. We have to find what is the total force exerted on this particle by this entire system. Got the question? We got the question. We have a small shell, we have a big shell, and in between there is a particle of mass small m. We have to tell what is the total force on this particle. Got it. Okay. Now let me start with a simple concept. Let's say we have a spherical shell whose mass is uniformly distributed. The mass is capital M, let's say. Now from the center, if we look at point which is outside the shell, there will be some gravitational field due to this entire shell. What is the value of gravitational field? Well, that depends on the distance from the center of the shell. Let's say this distance is small r. So this point A is outside the shell, and the gravitational field at point A will be given as G times m divided by distance square. You can see this formula is kind of the formula which we got for point particle. Can you notice that? Yes. So for all the points which are outside this shell behaves like a point particle. Great, great. But there are some points which are inside the shell. What about those points? Let's say this is point B. This is inside the shell. Well, for point B, there is no gravitational field exerted by this shell. The net gravitational field at point B is 0 due to this shell. Okay. So for the points which are inside the shell, this shell doesn't even exist. It does not exert any gravitational field for the points which are inside the shell. So EB is 0. So these are the concepts which we will use to solve our question. Now let's see what do we have. We have our spherical shell M1, and we have a big spherical shell M2. Now, point P is in between the shells. It is outside the shell M1 and it is inside the shell M2. Wow. Now let's talk about the magnitude of total gravitational field. By the way, the direction of gravitational field will be towards the center. Now, due to shell M1, there is some gravitational field at point P. What is the gravitational field? Well, we can see that point P is outside the shell of mass M1. So this shell can be taken as a point mass and we can calculate the gravitational field. This is G M1 divided by distance from the center whole square. So this is R1 plus R2 divided by 2 whole square. Great. Now let's talk about the outer shell. Due to the outer shell, there is no gravitational field at point P. Why? Because point P is inside the outer shell. So for point P, the outer shell does not even matter. Whether it is exist or not, it doesn't matter. So gravitational field due to the outer shell at point P is 0. Agreed? Agreed. So we can see after some little calculation, we are getting this gravitational field at point P. But we wanted the force on mass M placed at point P. So what is the force? Well, force is nothing but the gravitational field times mass. Okay. So let's multiply this entire thing by M and we will get the value of force. The magnitude of force is 4gm1 times small m divided by r1 plus r2 whole square. Great. So this is the force we obtained. Now let's see the options and we can see option C is the right answer for this question. A uniform sphere of mass capital M and radius capital R is surrounded by a concentric spherical shell of same mass but radius 2 capital R. So we have two concentric spherical shells. Great. A point mass small m is capped at a distance x in the region bounded by the spheres as shown in the figure. So we have a point mass small m. Now we keep this small m somewhere in between the spherical shells. Okay. So it is outside the inner spherical shell and it is inside the outer spherical shell. Good. The net gravitational force on the particle is. So what is the total gravitational force due to these shells on this particle of mass small m? This is the question. We have to find the total force on this particle. Got the question? Yes. Now let me straight away go to a important concept. Let's say we have a spherical shell, total mass capital M, which is uniformly distributed. Now there are some points which are inside the shell and there are some points which are outside the shell. For the points which are outside the shell, this spherical shell behaves like a point mass. So if we talk about the gravitational field on the points which are outside the spherical shell, this gravitational field would be towards the center of this spherical shell and it will have the magnitude gm by r square, where r is the distance from the center. Good. Now for the points which are inside the spherical shell, the gravitational field would be 0. So all the points which are inside the spherical shell, this spherical shell, whether it exists or not, it doesn't even matter. The gravitational field would be 0. Good? Good. But this gravitational field, which is for the points which is inside the shell, this gravitational field is 0 only due to this shell. Now in our question, we had two spherical shells. Now you can notice our point is outside the inner shell and it is inside the outer shell. So due to the outermost shell, the gravitational field at this point is 0. But due to the inner shell, there is some gravitational field at this point. So let's talk about the total gravitational field. The total gravitational field would be the sum of the two gravitational fields. Now if we talk about the inner shell's gravitational field, this small shell's gravitational field, we can say that as the point is outside the inner shell, this inner shell can be treated as a point mass. So the gravitational field is G capital M divided by distance from the center whole square. G capital M by x square. Now what about the outermost shell? Well, the point is actually inside the outer shell. Therefore, the gravitational field due to the outer shell would be 0. Okay? Okay. Now, we can find out the force. Force is nothing but the mass of the particle on which gravitational field is acting times the gravitational field. So this will give us the force, and we got our final answer. So let's see the options. Option A is the right answer for our question.